So the formula is C5H10O. When you already know the formula, the mass spectrum is sort of redundant, okay? The main thing you get out of the mass spectrum is the final signal. What's the final peak in a mass spectrum called again? Yeah, exactly. Your molecular ion peak, which means it gives you the mass of your molecule before it broke up. But if they already told you what the molecule is, you could calculate the molar mass either way. So it doesn't matter. Mass spectrum works if you want to look at the fragments, but until you know what the structure actually is, you don't know what fragments it could break up into. So in this case, we actually don't do anything with the mass spectrum at the start. We're going to go into your infrared spectrum. Infrared is easy. You compare it to your data sheet. So we have it open here. Now, guys, just do a process of elimination for me. C5H10O, there's only one oxygen. There are two functional groups in your HSC syllabus that it just can't be because it only has one oxygen and not two. It can't be. So we're just going to do, we're going to narrow our search as we're going. It can't be a carboxylic acid and it can't be an ester. Exactly. What could it be? It could be a ketone or an aldehyde or an alcohol. Yeah, exactly. So we're looking for this or this. Okay, so that just means that helps me not get confused when I'm looking at my infrared spectrum. I want to make sure all of my information aligns. Okay, there is a signal at 3000, but it's very sharp. It goes straight down. What is it? Yeah, it's just a single CH. You've got this here at, remember with infrared, it goes from right to left. So that's 1000, that's 1500, that's 2000. So this one here is about 1700. What's that one? Yeah, it's a C double bond O, which means you can narrow your search down even further. It's not an alcohol, it's going to be an aldehyde or a ketone. The data sheet for infrared spec doesn't distinguish between aldehydes and ketones, so we're going to have to figure that one out with something else. That's going to be it. This left-hand side here, what's this for? What's it called? The one before 1500? This is your fingerprint region, which they haven't blanked out. Mm, so we might as well have a look at it because it isn't blanked out. Before 1500s, only these last two. Now, the CC single bond is not unique. You're always going to have carbon-carbon single bond. So the only one we're concerned with in the fingerprint region, if it's not blanked out, is your carbon-oxygen single bond. Yeah. Which it can't be anyway, because you guys told me that we already know it's not an alcohol, so there shouldn't be a carbon single bond to an oxygen with a hydrogen. You also told me it can't be an ester, so there's no carbon oxygen single bond. So there shouldn't be a signal that's quite sharp in that region. So if you see anything like this, guys, this one's a little bit too short. Yeah, you want something that goes down a little bit more. So we can ignore these two. Nothing unique came out of the fingerprint region, even if they didn't blank it out. Okay. You've got your carbon-13 NMR spectrum. How many signals are here? 5. So remember the three things we're looking for? We're looking for chemical shift, which is the signals and how far left and right they are. We're looking for integration. And then the third one, do we look at this for carbon-13? No, okay. Splitting only shows up on a proton NMR graph. So for carbon-13, we're only looking at the first two. So you see 5 signals. Now, guys, how many carbons were in the original formula? Five. Okay. So what that means is you have five signals and you have five carbons. Every single carbon caused its own signal. Is there any kind of symmetry in the molecule? No, because if there was symmetry, then some of them would look like each other and they'd have the same signal. So the fact that there's five signals, five carbons, means that you're looking for something that's not symmetrical. Okay. You do have integration on a carbon 13, and integration is just how tall the peak is. The only thing is, though, you normally don't get told the integration for carbon 13. They normally just don't tell you. In this case, you don't need to be told the integration because we said five signals, five carbons, which means every single signal, each signal is integrated to how many carbons, guys? One. Yeah. So integration is how tall the signal is, which is how many carbons cause that signal. You've got five signals, you've got five carbons. That means each signal integrated to one carbon. So you normally don't get told the integration, which is fine. Okay. Now, carbon 13 and proton NMR, you get differing information for each of them. Okay. You don't get told integration, you don't have splitting, but there is one thing that carbon 13 that you get given for carbon 13 that you don't get given for proton NMR. What is it? Possible bondings? What do we mean? On the data sheet. Good. Carbon 13, you don't interpret as much yourself, but NESA gives you assistance with it. Yeah. So think of it however you like. Carbon 13 may be easier in that aspect. Who knows? So I don't have much to do myself with carbon 13. So carbon 13, I treat a little bit more like infrared. I just check the data sheet. So we'll just go left to right. You've got a 210, which is an aldehyde or a ketone again. We already know that, so this isn't too much more information. This, however, is an 8-mark question. You are going to mention it anyway in your exam to make sure you cover your bases, yeah? Even if it gives you the same information as infrared. You've got something at 70. Oh, sorry, read it wrong. Between 40 and 60 is 50. All right. There's five. I'm going to zoom in. The number 50, there's four, my bad. These four. The number 50 fits into all of these four ranges. Which ranges can you cross out based on what we already know? I can cross out the 25 to 60 because we know there's no nitrogen. Exactly. What else can I cross out? I can cross out 10 to 70 because I know there's no chlorine or bromine. And I can cross out 50 to 90 exactly because we already said there's no carbon oxygen single bond, there's no alcohol. It's also not an ester. All right, so that means it's this one. The only range left is this. Now, guys, if you were looking at this for the first time, when we did it together, we didn't know what it meant. You know now, though, it doesn't have the wording for you, which means they're testing you on whether you know it. They don't tell you what this is, but you know. The R on the left-hand side means what? Means an extra carbon. The carbon chain continues, exactly. So if I replace this R with a carbon, what does this look like now? This looks like a ketone, exactly, okay? So guys, be careful with this one. Most From what I've seen, most students don't find this out in class. You have to you get told, like you get told in class R is equal to a carbon chain, but most of the time they don't explicitly tell you that, hey, put the R in here and realize that it's a ketone. But you know now, yeah, this is your advantage. So that's a ketone, which means, right? And then your next signal, you've got something at 30, a little bit after 30. So we know now it's a ketone. So these ones here might just be another signal for this. We definitely know it's not the carbon nitrogen. So it might just be another ketone signal, or it might just be carbon-carbon single bonds. Yeah. So all of our unique ones are done. Okay, so we've got one extra piece of information. And then your proton NMR is where you get the most information. I'm going to slow down a little bit here because I know I got asked a question about it. They've given you the integration, which is nice. The integration should add up to the total number of hydrogens. Yeah, it was C5H10O. And you've got 2 plus 3 plus 2 plus 3. That is 10 hydrogens. Okay, so let's just look from left to right. Now, I got asked the question that was, like, how do I know what the bonding sequence is, and how do I know that it's a CH2 or a CH3? One comment about that. Now, give me a thumbs up if this makes sense, yeah? Actually, no, I'll ask you. When we did module 7, did you ever see more than one hydrogen on an oxygen? Ever. When you were drawing your structures and things like that, when you were figuring out names of organic chemicals, did you ever see more than one hydrogen bonded to an oxygen? Did you ever see something like this? No. Okay. What that means is if you see a signal integrated to multiple hydrogens, that group of hydrogens has to be bonded to a carbon. Can you give me a thumbs up if that makes sense? With the way oxygen bonding works, you don't see more than one hydrogen bonded to an oxygen. So that means if you see groups of hydrogens causing the same signal, it has to be a group of hydrogens bonded to a carbon. That's the first part. Yeah. Now, the only exception to this is, guys, when you did module 7, you can, but you can get a compound with multiple functional groups, but you'll never get, is that a separate question? That might be a separate question. You can get a compound with multiple functional groups. Yes, I think that might be a side question. But even if you did get a compound with multiple functional groups, each hydrogen is bonded to its own oxygen. They're not bonded to the same one. So if you see groups of hydrogens, it has to be bonded to a carbon. The only exception to this is what, guys? There was an element when you did it in module 7, there was an element that wasn't carbon that you could draw more than one hydrogen on. There's only one other element in module 7. Nitrogen, exactly. When you had nitrogen, you could do this. Yeah. So that's the only exception. So watch out for that. But most of the time, if you see groups of hydrogens, it's going to be a carbon. Okay. So what that means is if this is integrated to 2, it's probably a CH2. Yes, so you can get a ketone with an alcohol. Yes, depends on how much they want to test you. So that's a CH2. That's okay. That's a CH2, that's a CH3, that's a CH2, and that's a CH3. Okay. So the signal itself is caused by the H2, or the signal itself is caused by the H3. But it's bonded to some kind of carbon. Yeah. And then so that's the first part. You have to figure out what this gets bonded to, that's its neighbors, which you figure out from the splitting. Yeah. So the integration tells you what the group of hydrogens actually is, and then the splitting tells you what the next group of hydrogens is. Yeah. So then for the splitting, you use your n+1 rule. Uh, I'll answer that in a bit. Which n is your number of neighbors, and this is equal to your splits. So if you've got splits, you -1 to get the neighbors, yeah? So this one here is split into how many? Split into 3, so how many neighbors are there? 2. So if you've got neighbors, you add 1, but if you've got splits, you -1 to get the neighbor. So if it's a CH2 and it's split into 3, which means it's got 2 neighbors. And then guys, same thing. Yeah. If you have multiple hydrogens, it's not bonded to an oxygen. Now, there is a detailed answer for this. I got you to figuring that out based on reflecting on module 7. There is a detailed answer as to why oxygen doesn't form multiple bonds to hydrogen. The answer comes from year 11, module 2. Oh, sorry, not module 2, year 11, module 1. You have to draw your Lewis dot diagrams. You have to figure out how many valence electrons there are. We're not doing that here. Okay. So if you're interested in that answer, there is a answer based on first principles, but we don't go into that. So what that means is if you ever see groups of hydrogens, stick it next to a carbon. Okay, so it was a CH2 and then it's got 2 neighbors, which means its neighbors is another CH2. So then you're like, oh, this signal is caused by a CH2 and its neighbor is a CH2. So all you're going to do is put that together. So the first signal is caused by this, but it has this neighbor. So all I'm doing is putting it together so I can start getting a picture of what my bonding looks like. Okay. So to the person that asked that question, let me know if that makes sense and it's answering your question. If you have anything to say, then let me know. Well, that's the explanation. Yeah, so we're going to keep applying it. Your next one is a CH3. What's it split into? Right, good. Remember, you want it to go back down and back up, yeah? So if it doesn't, if it just branches down, then that's not a splitting. So have a look. So for this one, it doesn't go down and then back up. It's literally just one up, yeah? So that's going to be just a singlet, which means it's got no neighbors. So that's a CH3 with no neighbors. Okay. Now, when you've got something with no neighbors, what that could mean is it's bonded to a carbon with no hydrogens, or it's not bonded to a carbon at all. Yeah. So when you've got no neighbors, this is the situation. The carbon has no hydrogen, or it's not bonded to carbon. Okay. Which means it's probably bonded to any other atom, which in this case, the only other atom that exists besides carbon and hydrogen is an oxygen. Yeah. So sometimes you don't know which of the two options it is. Sometimes you can try to figure it out. Yeah. What bond did we say the oxygen was in this case? Double with carbon. That's okay. All right. So sometimes you can figure out which one of these two options it is, but sometimes you can't. Okay. You can remind yourself what you can do. So the two options are the neighboring carbon has no hydrogens, or it's not even bonded to a carbon at all, it's bonded to an oxygen. What you can do is remind yourself of what the oxygen looks like and ask yourself, is it possible for it to be bonded to the oxygen? Okay. So these are your two options, option one, option two. I'm testing option two at the moment. I'm going to see if it's even possible to bond to oxygen. Yeah. So let me pretend. So this is the CH3 of no neighbors. Let me pretend I'm bonding it to oxygen. Possible? No. Okay. Oxygen forms maximum two bonds. Yeah. Once again, Year 11 Module 1 explanation based on valence electrons. Da, 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 da. So it's not bonded to the oxygen. So this, you're trying to figure out what the neighbor could be. It's definitely not this one. So the neighbor must be this, the carbon with no hydrogens, yeah? So CH3 with no neighbors, the neighbor is going to be a carbon with no hydrogen. Now, guys, you can stop here, but you can start piecing it together as you're going, okay? When I labeled my hydrogens here, how many carbons did I already include? 4. There are 4 carbons here. How many carbons are there in the entire formula that they gave you in the question? 5. How many carbons am I missing? 1. What's that carbon? Which carbon am I missing? The carbon in the double bond oxygen itself. Exactly. Good. So I'm piecing together my information as I'm going, and I realize the CH3 has to be bonded to the carbon in the functional group. That's the only leftover option. Okay. So what that means is I'm like, oh, this is the CH3 and its neighbor is a COO. So I'm piecing this one together, and I realize my next fragment is a CH3 with a COO. Okay, so I'm starting to put it together. Third signal, you've got a CH2 because it was integrated to 2, and then we have to check the splitting for the neighbors. What's it split into? Uh, this one's a little bit misleading. Oh no, it's not 4. Look into it a little bit more. Yeah, it's 6. So there's this tiny little one here. It's a little bit blurry. One here, one here, one here, one here, one here. So there's 6. CH3, it's split into 6. It's a heptet, which means how many neighbors does it have? 5. CH2 with 5 neighbors. And I'm gonna walk you guys through it again. You might already know this. We're just gonna use our experience, yeah? When you did module 5, sorry, module 7, what was the maximum number of hydrogens on a carbon in an organic chemical? 4 when it's on its own, yes. So that's methane, but I'm asking in an organic chemical. Maximum 3, exactly. Whenever you drew an organic chemical and you were filling out the hydrogens, you could put a maximum of 3 hydrogens on it. So then what that means is if your neighbor is a number larger than 3, you're going to have to split it off, yeah? If it's a CH2 with 5 neighbors, that means it's got a CH3 group on one side as a neighbor, and the remaining, so you've got 5 neighbors in total. You've already considered 3. That means on the other side there must be a CH2. Okay, because there's no way you get a neighbor that's a CH5. From your experience in module 7, that's not possible. So you've got your CH2 in the middle, because that's a thing that caused the actual signal. And then we said, oh, it's got a CH3 as a neighbor on one side, it's got a CH2 as a neighbor on the other side. Okay, so let me just keep track. From the first signal, I got this piece of bonding that I drew myself. From the second one, I got this one. From the third one, I got this one. I'll deal with them overlapping later. I'm just going to get all of my information out first. And then the last one, it's a CH3. What's it split into? Yeah, it's split into 3. So how many neighbors do I have? 2 neighbors. So that's fine. That doesn't exceed the number 3. So that's going to be a CH3 bonded to a CH2 as the neighbor. Okay. That's it. That's the end of my question. I have to write my answer after that. So these are all of the fragments that you have. Now you have to figure out how they piece together. Okay. First of all, you want to make sure that you don't exceed the constraints of the question. The constraints of the question is any information you already have and any information they've given you. What they've told you is that the chemical formula is C5H10O. You cannot go above 5 carbons, 10 hydrogens, and 1 oxygen. Okay? So before I even start piecing my fragments together, I just want to make sure I don't go above the count. How many carbons do you see so far in all of my fragments? Eight. I've got one here, two, three, four, five, six, seven, eight, nine. So I've got 9 carbons, which means I've definitely exceeded what the question told me. What that means is it doesn't mean that my fragments are wrong. It just means that sometimes they overlap because you get a signal for one and then it becomes a neighbor and then that neighbor causes its own signal. Yeah, so you will get overlapping information. You're just using this check to confirm that. So you've got 9. I need to get rid of 3. Oh, okay. So help me out. Where do you see parts of the bonding looking the same? Those two itself are different. What is it similar to? Because if you want me to get rid of those, you have to tell me what it's the same as. Yeah. So this CH3, CH2 looks like this section, and then this CH2, CH2 looks like this section. So I could get rid of these two and still have it represented here. Okay. So what that means is I'm gonna get rid of I'm going to get rid of these two, and I'm just going to keep this. And then this one's unique. I can't get rid of that ever. So I'm going to redo my check. I don't want to get rid of too many and then end up having to work it out again. Confirm for me, do I have the correct number of carbons now? Yes. Do I have the correct number of hydrogens? Yes. Do I have the correct number of oxygens? Beautiful. So I've figured that out. All I'm going to do now is start piecing it together. And then what we said was you have to imagine where it's even possible to make a link, which means you work that off based off how many bonds a element can have. Yeah. So let's go element max bonds, which means how many lines can come out of it because a line is a bond. How many maximum lines come out of carbon? Hydrogen, oxygen, 2. Okay. This carbon in the CH3, how many bonds does it have? I'm not saying lines because I haven't drawn all of the lines, but how many bonds does it have? This carbon here. 4. It's it's bonded 3 times to hydrogen, and then it's got this line coming out. So that's already exceeded. What about this carbon on the right-hand side? How many lines coming out of it at the moment? 3, which means I can put one more line out here. This carbon, how many lines, or how many bonds does it have? 4, because it's bonded 3 to hydrogen and then a line out to the carbon. This carbon, how many bonds does it have? 4, because it's got 2 lines coming out and it's already bonded to 2 hydrogens. This one, 3, because it's got 1 line coming out and it's bonded to 2 hydrogens. So that's a total of 3 bonds, which means I can put an extra bond here. This question is actually simpler because there's only one spot you can make the link. Here. And that's it. So you're going to piece this together. You get a CH3, C double O, CH2, CH2, CH3. And then you just want to make sure that it matches your information. We already counted the carbons, hydrogens, and oxygen, so that's fine. The only other piece of information we got was the carbon 13. We said it's a ketone, not an aldehyde. Confirmed? Ketone, not an aldehyde? Yes, how do we know? Yeah, the oxygen isn't on a terminal carbon. Beautiful. Okay. And then you have to do your written response, determine the structure of the compound, which we've determined. So that's 1 out of 8. Justify your answer with reference to the spectra provided. So this is an 8-mark question. When the marks get longer, you get marks allocated for structure and cohesiveness. Yeah. So 1 mark is going to be for quality. So that's concise, logical, how you write your response. If the question mentions mass spec, then infrared, you should also talk about mass spec first, then infrared after. 1 mark for getting the correct structure in the first place, which means you have 6 marks left over for 4 graphs, which doesn't seem even, but your first 2 graphs you barely use. You just check your data sheet. Okay, so you get, let's say you get 6 marks, 2, 4. That means you get 1 mark for mass spec, you get 1 mark for infrared spec, and then it's only 1 mark because that information is less. You're going to get 2 marks for carbon 13, and you're going to get 2 marks for 1H, because those ones you did a little bit more work on. Yeah. Part of the quality of your response, make sure the structure between your paragraphs is the same. If you read carbon 13 from left to right, you should also be reading HNMR from left to right. It's things like that. Yeah. Okay, good.